In the video on Bell's inequality, we saw that this mathematical result turned out to be irrelevant by being more precise about the relation between microscopic and macroscopic physics. In this video, we will further explore this relation by turning Bohr's correspondence principle, which deals with the former, into the mathematics correspondence principle, which deals with the latter. In future videos, the mathematics version will turn out to be a cornerstone in most quantum discussions and interpretations. So let's start with Bohr's correspondence principle, which is something almost everybody agrees upon, at least no objections are known. And it is nicely general too. The background being, of course, that physics finally all boils down to humans having sense experiences, direct or in communication with each other, and these are classical in nature. On the physical side of the principle, Bohr himself took the step of specifying in classical terms by providing pictures of actual physical measurement equipment. In previous videos this was taken a step further by extending it with the microscopic to macroscopic transition with the accompanying illustration. And on the non-classical side, let's translate the phrase phenomena that transcend the scope of classical physics into phenomena that one has to describe with mathematics. Taking these two steps together, one gets this, the mathematics correspondence principle. It may be necessary to use mathematics, but then you must take great care that this mathematics has a relation to the real world, to physics. It is more than easy to make something in mathematics that has no meaning in the physical world at all. The previous video on Bell's inequality and its related measurements provide an excellent case for taking the two side by side. On the left you have an illustration of the calculations that lead to the inequality, and on the right a practical representation of the measurement part of the case. And from this combined illustration, one can also immediately see what the way is these two worlds communicate. The outcomes of the calculations are numbers, and the outcomes of the detectors are numbers. Which might seem very natural, but also hides a problem. And this next simple illustration reveals the problem. The numbers of physics are not the same as those of mathematics. The numbers of physics are of the kind amount is number times dimension, as on the left in the illustration. The mathematical numbers are barren numbers, on the right. And if one starts calculating with physical numbers as if they were mathematical numbers, things go wrong. One cannot add numbers having different dimensions, as one learns at high school. If you just allow addition, numbers can have one and the same dimension. But if you also allow multiplication, they cannot have any dimension at all, as the illustration shows. Coming with an inevitable conclusion, there's a rift between physics and mathematics, and this rift seems fundamental. So any statement that equates the two, of which this is an example, makes a fundamental mistake. Ponder on this for a second, and you realize that this also goes for those by Bohr, Heisenberg, Born, etc., when they are trying to say mathematical-like things about quantum mechanics, as here in the words of the YouTuber Part G, who summarizes it perfectly. And here is an even shorter one that also can be heard frequently. It is highly unlikely that this is true. Nature doesn't solve differential equations. But that of course is just the opinion of an old-fashioned physicist. But take a step back. Everybody realizes that the wave, the physical thing, is not the same as the wave function, its mathematical representation, and let alone the state, and the other way around. That is totally obvious once you say it out loud or write it down. The other two are abstractions of the first one. Abstractions always lose information. In this case, as will be shown, vital information. Here illustrated with the representations. Each step towards the right loses a ton in information. Information here in the sense of physical detail. The first one has an origin, a phase, and an amplitude distribution saying something physical. The second one is the wave function obeying the Schrödinger equation for a particle having a constant velocity. It just has a phase and a constant amplitude that says little or nothing. The third one is just a symbol, a distribution of black spots on a white background, which could be replaced by any other distribution without changing meaning. For the most abstract one, here illustrated with the double slit experiment, symbols don't have a phase, so there is no interference. If the state is identical to a wave function, don't use the concept of state. Here's the representation through mathematical wave functions obeying the Schrödinger equation for a particle with constant velocity. Here there is interference due to superposition, but no physical interaction, because the definition of superposition is the absence of interaction. After the area of superposition, waves propagate as before. In this representation, the wave-particle duality, wave function collapse, and a measurement problem pop up, due to an incomplete physics to mathematics relation. And here's the complete physical picture corresponding to the permanent Dirac-like waves associated with particles, which then have to include those of the equipment. The interaction is due to the reflected waves, which waves for all the particles in the equipment, leading to the explanation of all known phenomena in a physical way. All leading to this summary of the three levels of representation. Within the top row, the representations at the different levels of applying the mathematics correspondence principle, and at the bottom one how they work out for the double slit experiment. The states explain nothing, the abstract wave functions explain the interference, and the permanent microscopic waves and the two-particle interaction explain it all. This as a bonus, Bohr's correspondence principle in mathematical form. The psi in the top left panel of the previous illustration gives a state that represents the outcome as recorded by the measurement equipment, or Bohr's classical state. And at the bottom right, what has to be described using mathematics, the microscopic two-particle wave functions phi having complex phases. The infinity involved in the latter can be seen to stand for a phase transition. Physically, a phase transition is a point where things get so large that new phenomena appear or that existing phenomena disappear. The old version of the disappearance of quantum phenomena was recently heard again. The classical world doesn't notice quantum effects because the mass in lambda is h divided by mv is very large, so the wavelength is very small and too small to notice. The mathematics is right, but the physics isn't. The argument of small wavelength assumes silently that the waves of all microscopic particles contribute identically, that is, that the waves are coherent, as on the left. The physical reality is, of course, that due to relative movement of the particles, the waves are totally incoherent, as on the right, which is an effect that works much faster. These incorrect applications of Bohr's correspondence are compounded in the application of the mathematics correspondence, due to the earlier mentioned ideas about the primacy of mathematics, leading to the known problems in the physics talk around the mathematics. Here's the probably most famous one, Schrödinger's cat paradox, with on the left the well-known physical version and on the right the slightly lesser known mathematical one. With this example, Schrödinger exposed a violation of, or lack of, the mathematics correspondence principle. And this is a second and more recent example. The screenshot shows Roger Penrose criticizing the method of decoherence to solve the wave function collapse. What he notices is that the physical concept one gets from the mathematics is not the same as the one put into it, a direct violation of the mathematical correspondence principle. The upcoming series on the quantum interpretations will see more examples of such violations. The proponents of each specific version can start trying to guess what the objection will be. On the positive side, this author is working on a list of rules for the mathematics correspondence principle. If you have any suggestions, please leave them in the comments. If there is a sufficient number of items, the list will be published separately with the chosen affiliations. The next video in the series will probably be on a specific aspect of the relation, how to deal with infinities.